Welcome back to the deep dive. Today, we're really getting into the weeds with a specific sequence from the OEIS.
We are indeed. It's A00261.
Right. And the definition, it looks straightforward enough. AN, nan N1 plus N3, AN2.
With the starting points A182.1.
And if you list out the first few terms, you get 0, 1, 3, 13, 71, 465. I mean, they shoot up really fast. 3, 5, 39, 3, 0, 6, 3, 7.
They certainly do. That growth is part of the story.
So our goal today is to unpack this. We'll look at the recurrence itself, some really cool combinatorial interpretations, and the math formulas behind it. Think of it as a shortcut, maybe, to understanding how these number sequences connect to bigger mathematical ideas. Lots of aha moments, hopefully.
Absolutely. What's quite fascinating, I think, is how such a simple-looking rule, this recurrence, can generate numbers that have, well, incredibly rich structures hidden inside them.
Structures that connect across different fields.
Exactly. That's the beauty of something like the OEIS, Neil Sloan's encyclopedia. It acts like this huge map showing connections you might never expect. Every sequence really does have its own unique story.
Okay, so let's start with that story's beginning. The recurrence, AN-1 plus N3, AN2. We see the numbers grow fast. What specifically in that formula hints at that kind of explosion?
Well, the coefficients are key. You have n multiplying the previous term, AN1, and N3 multiplying the term before that, AN2.
Right.
That factor of n in the main term, nan1, is a strong indicator. It often signals growth related to factorials, n or something similar, which, as you know, grows extremely rapidly.
Okay, so the n points towards factorials. What about the N3?
The N3 term adds, let's say, a twist. It modifies that factorial-like growth, mixing in a kind of polynomial behavior. It's this combination that really drives the acceleration we see in the terms.
And does that combination hint at what it might be counting? Factorials often pop up in counting permutations.
Precisely. It strongly suggests a combinatorial origin. And just a note on indexing, the OEIS lists this with offset 1, 3. So A1 is the first term given, A2 the second, but the third term listed is a 3. Some formulas might use slightly different conventions, starting at 0 or run of 1, which is common.
Got it. So the recurrence gives us clues about the growth and maybe the type of problem it solves.
Yeah.
But let's get to the really interesting part. What does it count? This is where it gets tangible.
Right.
The first interpretation mentioned is quite algebraic. It connects to the permanent of a 0-1 matrix, specifically a permanent of an n by n plus 3 matrix filled with zeros and ones, with some condition about n zeros not being on a line. This comes from Jap Spies, building on work by Song et al. So, okay, permanence. For our audience, maybe refresh us quickly. What is a permanent and why are 0-1 matrices important here?
Sure. So the permanent of a matrix, it's calculated much like the determinant. You sum over permutations, products of entries. But crucially, you don't alternate signs. All terms are positive.
Okay, no minus signs.
Exactly. Now, 0-1 matrices with just zeros and ones, are fundamental in combinatorics. They often represent relationships like adjacency matrices of graphs, specifically bipartite graphs.
Oh, okay.
And the permanent of the adjacency matrix of a bipartite graph, it counts the number of perfect matchings in that graph.
Perfect matchings, like ways to pair up all the vertices?
And that's precisely.
Yeah.
So the connection of A0000261 to this specific type of permanent means our sequence is literally counting these matchings or related structures in a particular matrix setup. It bridges this abstract sequence with concrete problems in, well, both linear algebra and graph theory.
That's a neat connection from numbers to graphs via matrices. Now, there's another interpretation, and this one sounds, well, wonderfully quirky. The beads, necklaces, and cords problem.
Ah, yes, that one's quite visual.
It says AM plus 2, so shifted index equals BN for n at least 1. And BN counts ways to distribute n distinct beads, labeled 1 to n, onto two kinds of things. Unordered necklaces, but you can't have a necklace with just one bead.
That exclusion is important.
And 3 indistinguishable but ordered fixed chords. It even adds that empty necklaces or chords count as a factor of 1b0 is 1. This comes from Wolf-Dieter Lang, inspired by work on, of all things, quark and gluon diagrams by Mullins-Schnodal.
Physics connections, too. Fascinating.
It is, but okay, this description is dense. Labeled beads, no single bead necklaces, 3 special chords. How do these pieces fit together?
Let's break it down. First, labeled beads. This immediately tells us permutations are involved. The identity of each bead matters.
Okay.
Second, the unordered necklaces, excluding single bead ones. This no single beads condition is key. It points directly to derangements, permutations where nothing ends up in its original spot. These are counted by the subfactorial numbers, sequence A000166.
Ah, subfactorials, right. A000166.
Exactly. Third, the three indistinguishable ordered fixed chords. This part relates to another sequence, A000000160. Specifically, its terms sometimes denoted C3N. They count arrangements on these specific chord structures.
So necklaces involve derangements, A0000166. Chords involve this A0000163. How do they combine to get BN?
They combine through what's called an exponential convolution, sometimes also called a binomial convolution. It's a standard way to combine generating functions or sequences where labeling matters. Essentially, BN is built by combining the counts from A0000166 for the necklaces part and A0017110 for the chords part in this specific way.
A convolution, like blending them together based on how many beads go where.
Precisely. And this structure leads to its own recurrence for Bn, which is slightly different from the one for An, Bn plus 2, Bn is 1 plus Na is 1, Bn 2. With B1, 0, and B1, it elegantly weaves these different combinatorial ideas, permutations, derangements, specific arrangements into this single sequence Bn, which then connects back to our original An.
That's quite a construction. Well, let's try to make it concrete. The example given is for N4. We know A6 from our sequence is 465, and this problem says A6 should be B4.
Correct.
The explanation uses weak two-part compositions of 4, 4, 0, 3, 1, 2, 2, 0, 4. These seem to represent splitting the 4 beads between necklaces, first number, and chords, second number.
Yes, that's the idea. How many beads go to the necklace structures versus the chord structures?
Okay. And the 103 case is missing.
Ah, because you can't have just one bead on a necklace.
Exactly. That exclusion rule eliminates compositions where the first part is 1.
Right. So can you walk us through one of these, say 3-1? How does that specific split contribute to the total count of 465?
Okay, 3-1. This means 3 beads go onto necklaces, 1 bead goes onto the chords.
Got it.
First, choose which 3 beads out of the 4 go to necklaces. That's binomial 403 ways, which is 4.
Choose 3 out of 4. Makes sense.
Then arrange those 3 chosen beads onto necklaces as derangements. No single bead necklaces allowed implicitly. The number of ways is the subfactorial SF3, which is 2.
Okay, SF3.
Then the remaining 1 bead goes onto the chords. The number of ways to place 1 bead on those 3 chords is given by the relevant term from A00171, which is C31 is 3.
So C31 is 3.
Right, so for the 3-1 case, you multiply these parts. Binomial 4 format the SF3C31 equals 4, 2, 3, 3 equals 24.
24 ways for that specific split.
Exactly, and you do this for each valid composition. Let's quickly check the others. 4-0. Choose 4 beads. Binomial 4-1 arranges derangements SF4-9, 0 beads on chords, C3-0-1 usually, so 1-9, 1 was 9.
All right.
Choose 2 beads. Binomial 4th arranges derangements SF2-1, 2 beads on chords, C3-2, so 6-1, 12, 72, and 0-4. Choose 0 beads. Binomial 4-1 arrange 0 as derangements, SF0-1, 4 beads on chords, C3-4, 360, so 1-1, 360 equals 360.
Perfect.
And if we add them up, 9 plus 24 plus 72 plus 360, that is indeed 465. Wow!
It clicks, doesn't it?
It really does. That example makes the whole beads and chords thing crystal clear. It shows how AN isn't just abstract, it's counting these very specific, if slightly unusual, arrangements. That's a great aha moment.
It is. Giving numbers a physical or structural meaning is often very eliminating.
So we've seen the recurrence, the matrix connection, the beads connection, but A00261 also lives in the world of analytical formulas, right? Generating functions and such.
Yes. Absolutely. Beyond counting, we can describe sequences using analytical tools, which often reveal different kinds of structure or allow for things like approximations.
What's the main tool here?
One of the most powerful is the exponential generating function. For A00261, using a slightly adjusted offset, starting at index -1, the EGF is remarkably compact. XPX 1/4.
XPX 1/4. Okay, what is having a nice EGF like that? Tell us.
Well, XPX is EGF for derangements. A000166, essentially. And 1/4 is related to combinations with repetition or sequences involving powers. The fact that the EGF is a product like this reinforces that convolutional structure we saw in the beads problem. Generating functions encode the sequence's entire structure.
So the EGF echoes the combinatorial interpretation. Are there other formulas?
Oh, yes. The sequence pops up in various forms. There's an explicit formula linking it back to the subfactorials A000166, found by Vladeta Jovovich. It's a linear combination of 4 consecutive subfactorials.
Interesting, a direct algebraic link.
Exactly. And then for, say, estimating the size of terms for large N, Mark van Hoge provided an approximation using the gamma function and XP01. It gets remarkably close.
Useful for asymptotics.
Very. And for exact values, Peter Lushny gave formulas using hypergeometric functions, like AN hypergeometric 4n plus 2, 1n. This connects the sequence to a whole class of special functions. There's even a continued fraction representation by Sergei Gladkovsky.
Wow. Hypergeometric functions, continued fractions. This sequence really gets around mathematically.
It does. The existence of all these different descriptions, recurrence, combinatorial models, generating functions, hypergeometric forms, highlights how deeply embedded it is in various mathematical structures. Different tools reveal different facets.
It's quite impressive. And the OEIS itself makes working with this easier, right? It lists Maple and Mathematica code snippets.
Yes, that's incredibly useful for computation and exploration. It shows how mathematicians actually interact with these sequences day to day.
And the references, links to papers, classic books like Berwaldi and Reiser or Riordan on combinatorics. It really is a gateway.
It truly is. A single entry can be a starting point for exploring vast areas of combinatorics, number theory, and special functions.
And it connects outwards too, doesn't it? You mentioned the cross-references.
Absolutely. R0000261 is linked to A000166 subfactorials, A000161, A00030153, dozens of others. It emphasizes that these sequences don't live in isolation. They form this intricate web.
Understanding one helps understand the network.
Precisely. It's a beautiful illustration of the interconnectedness of mathematics.
So let's wrap this up. We started with AN plus N3, AN2, saw it grow incredibly fast. Then we found it counts configurations related to matrix permanence and also these elaborate arrangements of beads on necklaces and cords.
That beads example really brought it home.
And finally, we saw its analytical side, the elegant EGF, the connections to subfactorials, hypergeometric functions. It really demonstrates the richness packed into one OEIS entry. For anyone studying number theory, this hopefully gives a quick way into understanding A000261's layers.
I think it perfectly highlights how math isn't just about finding the answer. It's about uncovering these beautiful, sometimes surprising, relationships between different ideas. The journey through A000261 shows that wonderfully.
A great takeaway.
And perhaps something to ponder. How many other sequences, defined by just a simple line of recurrence, are out there hiding similar layers of combinatorial meaning or analytical elegance? What seemingly simple patterns might hold unexpected complexity, just waiting for someone to unpack them?